Welcome to Natural Habitat Adventures Daily Dose of Nature. Today's presentation, The Aurora Borealis Through the Ages, Part 3, Science and Discovery, is brought to you by NatHab Expedition Leader Kristina Disney. Kristina earned a double major in biology and physical geography from McGill University and has published research on nitrogen fixation and sphagnum moss in the journal of Botany. She conducted extensive remote field work from studying marine mammals in New Brunswick to carbon dioxide and methane emissions research in the subarctic and biodiversity monitoring in northern Alberta. Kristina now divides her time between soil sampling in Labrador and the Yukon during the summers, guiding polar bear tours in Churchill each fall, and working towards her PhD when at home, which she isn't now. Kristina, good to see you. The show is yours.
Thank you, Rob. I know I really got to stay home if I ever want to finally have this bio turned into a completed PhD, and that can be a past tense phrase, which I am going to do. 2026, folks, I'm turning over a new leaf. We're going to shift gears and try and get that done. But for now, I'm still happily in guiding mode and happy to be here with all of you. So thank you so much for tuning in. Rob does really great intros, so I won't spend very much time talking about myself, but I do just want to backtrack a little bit. For anyone who's tuning in for today's webinar, there are two previous ones. And so I won't go through them entirely, but you're welcome to jump back for them if you want. The first one I did all the way back in November, just the way time worked out, we've had this one spread a little while, was really about culture. It was about how these phenomena are integrated into cultures sort of all around the world, from our earliest known records all the way up to present day and things like that. The second one was more so about sort of the shifting into empirical science in the 1700s and all these crazy wild theories that we've gone through trying to figure out what are the aurora, how do they work, what in the world is going on. And it was a cool era. I mean, I'm very jealous. I'm obviously grateful to be born at a time with penicillin and Wi-Fi and things like that. But if you're a naturalist now or a guide, there's like, even just thinking about, there's little hairs that come up on the back of my neck on the idea of being able to be this sort of all-encompassing scientist. So I'm going to use Halley here as an example. Edmund Halley, most people know him because of Halley's Comet. Back then, if you studied one thing, you kind of did, you were just more broad. Everyone was kind of less siloed. So one of the wild theories I wanted to just highlight from before is that they used to think at one point in time that the Northern Lights were actually this off gas of sulfuring from a subterranean second Earth underneath. So the Earth was hollow and it was this other atmosphere that was escaping into the air and causing these lights to go off. A little bit Journey to the Center of the Earth style. And so that's just a little tidbit. I couldn't help myself of bouncing back into one of the fun, crazy theories. But we kind of talked about, we talked about culture and stories. We talked about, I'm going to call them like the stories of science that didn't pan out. You know, again, as we try and solve things, all theories are good theories until we find out there's a better one, really, right? And so while this might sound quite ridiculous to you and I, to be thinking about an Earth that is hollow because we know that it's not, an Earth is full of magma and molten rock and all that, you know, until you prove it wrong, it seems like a good idea. So I'm going to pick up where I left off with some of that sort of era discovery into a really big event that kind of shifted into it. And I meant to ask this of Rob beforehand, so I'll ask it now. I'm going to go through some heavy science, folks. Even for me, I am not a trained physicist. And so a lot of this stuff, even for me, I really got to take some time to like gel through it. And I am happy to repeat things, especially some of these bigger concepts. So this is an invitation for Rob. If this sounds good to you, Rob, you can give a little hey. But if people have questions along the way, I'm happy to sort of stop and just iterate it again in the moment, because it takes, you know, lots of stuff we need repetition to read, but this is it's literally a little bit of rocket science, jokes, no jokes, right? So we'll mix some of that in. And then also, if there are any physicists out there in the audience right now, please cut me some slack. I'm doing my best. I'm actually a biologist masquerading as a hydrogeologist, masquerading right now as a physicist. So we're wearing lots of hats. Some of them we've earned, some of them we're just doing our best. Okay, 1, 2, 3 should bring us into the present. Actually, it doesn't bring us into the present. we're going to go back in time. We're going to go back to 1859. This is right where I left off at the end of our last webinar. We're talking about the age of discovery. We kind of made it through the 1700s into the 1800s with lots of crazy things happening. Because we're getting the ability to measure things more accurately. Soon photography will be invented, which completely changes the way we understand aurora. Because for the first time, it's not just people's drawings that we use, but we can actually like compare them. We can figure out height and distance more accurately because we can triangulate it. But I want to hone in a little bit earlier than that, and I want to hone in on 1859. And what happened that fall was this crazy aurora. Like people nearly at the equator, I think at like 11 degrees latitude, like saw the aurora. They saw it in wild, crazy colors. And at the time, we have technology now that actually interacts with the aurora. So we have telegraph lines that catch on fire. There is so much electricity going on in the air. We have other ones. There's a really cool example from in Boston, which are unplugged and the operators are still sending messages because there's that much of a geomagnetic storm interacting with them. And this event is kind of this, like, it's the honing point, it's the tipping scale from when we go of all these different theories of understanding aurora and what causes them and how they work, to finally having a concrete thing that we then build off of all of our following science. So the reason why we call it the Carrington event is because there was a gentleman named Richard Carrington. He was we'll call him an amateur astronomer, and you can actually see what he was drawing back in the day. So on September 1st, I believe, he was drawing sunspots. So that's what this little, I mean, I know it looks like a doodle. It may not seem very exciting to anyone else, but this is a big deal. He was drawing these sunspots. And when he was doing so, all of a sudden, maybe I'll just flash forward really quickly so you can see how we did it, and then I'll go back. The way that old school way of drawing sunspots, and you can still use this today, is you essentially have like almost like it'll project what the sun views onto a wall. You can see this is a much more recent version here. You can see the original Richard over here on the right, excuse me. But essentially you would have it project onto the wall, and then you could sit there and just sketch and trace them as you saw them, right? And so he was doing that, and he got blinded by this crazy solar flare. And then roughly 18 hours later is when this wild storm happens. This geomagnetic storm, aka wild showing of aurora. And it clicked in his head. He was like, oh, this is what causes this, right? Like, it's not some subterranean gas, it's not light reflecting off of the snow. And people had different theories about it beforehand. Like, I'm not going to say that he pulled this idea, out of thin air, but it was the first real kind of solid evidence that people had for this. And so if you want to know more about the history of the science, you can jump back to the previous webinar, but we're going to kind of go from this moment forward. There's one more aurora scientist I want to give a nod to before I kind of jump into the science of aurora. Again, if I was to think about the 3-part webinar, the first one is like the stories of aurora. The second one is the stories about the people who have studied the aurora, right? And so this last one is, I'm going to take the people out of it. Sometimes I don't like how objective science becomes, because the way we know something actually does quite affect what we actually know. And so this is going to be a bit more classic sciencey as I skip out of, after this one quick nod here, and into more just what we actually know, not about who discovered it or the relationships of it, but just what do we know now. It's nice to interweave them, but sometimes it's easier to put them into different boxes. But just keep in mind, if you have been following along, that all of the cool things I'm about to tell you are hours, years of people's lives in order to figure that out. And I think when we value knowledge that way, it has more meaning when we choose to do something with it, when we choose to engage with it. So same thing with art. I do the same thing in art museums. So it's how I like to look at art, as the hours of someone's life. But anyways, there's one more aurora scientist I want to talk about before we get into the nitty-gritty of the nerdy. And it's a Danish gentleman. You can see a picture of him here. This is some old school aurora viewing equipment. They're trying to triangulate height back in the day. They'll have different mirrors, and they're setting stuff up. He would have been most of his life would have been pre-photography. So again, he would have been sketching, things like that. So this is kind of one of his faces that he's getting taken a picture of. And this fellow's name is Sophus Peter Trumholdt. So he was alive from 1851 to 1896. So remember I said the Carrington event would have happened when he's 8 years old. He's a kid. So that means that, like, kind of the anchoring key points of how to understand the aurora are existing before he sort of comes up in the world. And the reason why there's also so many other great scientists who I'm not going to mention, not because they don't have great stories or things like that. I'm just cherry picking him because he was an amateur scientist. He was a Danish school teacher. And eventually he gets enough grants to go off and do this full time. But he loved the auroras so much that he basically just figured out a lot of this on his own. He was self-taught. And I think that we forget that, this can just be you, right? The guy who found all the snowflake shapes was just a kid in the backyard with a microscope. Science is, we put it on a pedestal, especially space science and things out in the world, but lots of times we can just be everyday people who figure out really cool things. So that's why I wanted to bring him up. And he was one of the first people who coordinated a sort of like a large area-wide observations of the aurora. He had it going all over Scandinavia. He was the first one to document further relationships between sunspots. So what Richard was drawing, Carrington was drawing, and like daily and seasonal cycles of the sun with aurora. So he could start essentially showing these relationships. It was the first breadcrumbs to what you and I are going to learn about today. And also, he was the first one to kind of document what we call now the aurora oval. So again, it's kind of that shape and that arc that we now know to look for and sort of project within. So very cool self-taught scientist. Wanted to give a nod to him before rolling on. He was also, just one last one, in his time, he really wasn't acclaimed. There's not a lot of stuff that was known about him. He's sort of been talked about more posthumously because he was never affiliated with the university. That's kind of why I like him. Maybe that's why he's my unsung hero, is because all these other guys, would have positions in the scientific societies, or they would get promoted or things like that. And he just went about freezing his butt off through all of Scandinavia recording this because he really loved it. So shout out to an original aurora pioneer. All right. So what we're going to talk about today, and we will eventually get to Earth. I promise we will get to Earth, but we need to start away from Earth. We need to start out near the sun and work on that. And I hope one thing I can transfer to everyone listening today is sort of an epiphany that I had while building this out, is that there really is space weather, not like a metaphor, but we think about, you look at the sky today, it's cloudy, it's rainy, it's whatever, right? We're used to Earth having all these different temperaments. And I think that space is this big, vast thing that the average person thinks about as, yes, we're moving and we're circling and we have orbits, but we think about it as relatively constant. Weather is not a constant. The only thing constant about weather is that it's changing. So I hope that when you're done this, you can really think that our Earth, our relationship to the sun, and the sun itself is not a constant. It is always changing. It is always giving us different forms of weather. And they call it space weather, right? We'll roll through all the little kind of boxes that you're seeing here. Don't worry if you can't read them. But we're going to talk about this, great, right from kindergarten. We're going to start with the sun. And the sun is a big deal. Like jokingly size-wise, it's 100 times bigger than we are. And we talk about how lucky we are to have our sun because it's life-giving and it has, Earth is really just, it's like Goldilocks. We're not too far away from it. We're not too close to it. So we're burning up and we're not freezing. We get our light from it, which gets here in like 8 minutes and 20 seconds, which is crazy when you think about it because it's 93 million miles away. These are all numbers that like I can't conceive. I'm not going to pretend that when I say to you guys 93 million miles, oh my gosh, I have no idea really how far that is, right? Because as a human, we can't really comprehend just how big that is, right? Like look at little Earth. You can see Jupiter, you can see Saturn, and little Earth is a little teeny tiny dot down there, right? Like these are things that sure we can do the math of, but it's not something we can feel, taste, touch. We can't sensory understand it. So it just feels unbelievable. But it's real and it's happening. It's an old yellow dwarf star that's been hanging out for 4.5 billion years. And it's got lots of hydrogen and helium. And it's just a massive scale of explosions. And those explosions are what gives us life, right? Creation, a cycle, life and death. And again, it appears this, even in this picture, right? We see it as this constant, unchanging source of life, but it's dynamic. It's continually changing. Those explosions are never the same twice, something's always going on. So sort of as a joke, but thank your local sun. Take a quick moment, give a little shout of gratitude. It's like shopping local, be grateful we've got the sun that we have. So the structure of the sun is kind of ultimately going to get to how we get aurora. So just hang in with me here. We're gonna go from beginning to end here. So same as us, it's got a core. Its core is really quite hot. We're looking at 27 million degrees Fahrenheit. Again, it's a number I can verbalize, but I can't even imagine. Like my thoughts would incinerate. Forget about my body, right? Like it's so hot, it's unbelievable. And then it cools and it gets to the surface of the sun. Now here's a fun thing that's kind of crazy. So what they call the outside of the sun is actually called the photosphere. That's where we get our light from. Photo, light, very good. And then the outside of that is what's called the corona. And so that's kind of the sort of hazing. Does it have it up on? Yeah, there we go. The sort of hazing light. So whenever we have an eclipse, and if you're lucky enough to see one or to watch one, right, and you see the shadow of the Earth pass in front of the sun, but there's still the light ring around it, that's when we can actually see the corona. The center of the sun is usually so bright that it outshines it, but when you take away the center, you can actually see the light emitting from itself. Here's one of the fun mysteries of the sun. For some reason, the corona is actually hotter than the surface. So it's like core is hot, then the surface is cooler, and then its atmosphere is even hotter, or equivalent of an atmosphere. And so that's kind of the beginning of it. And this is also where I want to continue that metaphor, or not metaphor, the reality that like space, weather, even though we're 93 million miles away from the sun, we're actually kind of functionally still in the atmosphere of the sun, right? We are getting wind from the sun in the form of plasma, in the form of these hydrogen electrons that are escaping from it. And so we're not just getting light from it, we're getting particles that are blown massively in our direction from all of these explosions. And so we're interacting with that. And that's kind of we're getting into it now. We're getting closer, right? So here's our sun. A lot of that material is exploding and escaping in all directions. We just care about right now the stuff that's flying at us. But remember, the sun's a nice big sphere. It's going around every which way. And so as it escapes, it's this huge magnetic bubble that it gets sent out, and all that magnetic energy is traveling with that wind, with those particles, and it's ionized. So what that means is that, yes, there's a hydrogen and an electron, but they're not hanging out. It's just like it's so much energy and it's so hot that it's just this big soup that's flying out at us. Or wind. Let's stick with the wind analogy. We'll save the soup analogy for a little bit later. Okay, so that's getting carried towards us. Now, the sun has a few different ways that it's kicking out energy towards us and at us. And these are kind of the different sources of solar wind. And again, think about our different storms here on Earth. We have hurricanes, we've got our jet stream, we have just your average rainy day. Keep those parallels in your head, because that's kind of the same way we can get different forms of solar wind, different intensities that come at different times in different seasons, right? It all sort of feels the same. So we'll start with sunspots, because that's kind of where we started before, right? So sunspots, what Richard Carrington was drawing, we see them as black on the sun. Really, they're not devoid of light. It's just that the rest of the sun is so crazy bright that it looks like it's a shadow. But these are spots where the sun is cooled a little bit, and you've actually got this big tangled mess of electromagnetic energy. And eventually the tangle can get overwhelmed, not always, but it'll get so overwhelmed, it'll go. And that's when we get the thing on the left side of the page, which is the coronal mass ejection. So remember I said we have the sun, and then when there's an eclipse, you can see all the energy around it, and that's actually plasma and electrons flying out. It's always sort of free flowing. There's always some wind coming off of it. But because all of the sun is this sort of molten mixture of energy, think about it as you can, has anyone ever played that game where you're a kid and everyone grabs hands with the person next to each other and you try to unravel? And sometimes you can, right? It's sort of amazing because everyone grabs a hand and then you have to lean over each other and jump through someone's legs. And it's a really fun game to usually do for team building or with kids. If you haven't played it, highly suggest it for your next work retreat. Get up close and personal with people. It's post-COVID. You should be fine. But sometimes you can't. No matter how many times you unwind, at the end of the day, just the random way that you grabbed each other, you can't let go. And so think about the magnetics thing like that. The magnetics will get all raveled up, and then eventually you'll hit a point where it's like, I can't untangle, so it blows up. And that's when we get these crazy amounts of energy and plasma sent our way. And we like Aurora because it sends a big, bad batch of energy towards us, which will create a lot of exciting things once it hits our magnetic sphere. So those coronal mass ejections are often associated with sunspots because sunspots are spots where energy is tangled, right? So we see those, and we'll talk about this, but we see those during solar maximums, and I'll talk about those a little bit later. On the bottom side of the chart, so solar prominence or filaments, those are kind of like, again, that sort of same tangled thing. It's less of a tangle, but those can eventually also tangle up and turn into coronal mass ejections or send energy out on their own. And then coronal holes are different. They're kind of cool. We see those more on solar minimums. And again, I'll explain the contrast between maximum and minimum in a little bit, just a little further down the line. But those are like, just imagine a hole, like your windshield's open, right? And all that energy. So these don't have an explosion. These are like, there's a hole in the way that coronals work, and it's actually just spitting out a boatload of energy, but it's more consistent. So those are cool for solar storms. You get more of a moderate storm out of that, and it's more consistent and it lasts longer. So you could have, like, you know, a longer viewing at a lower intensity on an aurora side, whereas on the CME, the coronal mass injection side, you might have a shorter viewing, but oh my gosh, is it going to be booming? It's going to be really cool. So if we go back to 1859, that's what they had. They had a coronal mass ejection. They actually had the largest one we've ever recorded since we have instruments to record these things. There could have been some bigger, badder ones in the past, don't know. But there was this huge amount of energy that came. So he sees the sunspot. 17, 18 hours later, all that energy hits Earth, and we get these crazy showings. We get all the colors. You can see it all the way down the equator, right? So those are the ones that we get excited about. And these, we now have the technology to predict them far enough in advance that it's reasonable to, right? So, you know, you can let someone know 24 hours ahead of time, hey, most likely there's going to be a really cool aurora in the next day. That's when you're seeing your now weatherman, or you're reading a news clip about it. This is how they're able to give you that 24, 30 hour, well, depends how fast they're going. Sometimes they're really quick. Sometimes it's half a day to a day, but that's why they can give us the heads up now. Okay. So that kind of hopefully grounds us in how awesome our sun is, point one, and how the sun is always emitting energy at us, but that energy is variable. It can be big, bad, small, subtle. It's always coming, just like we always have weather here on Earth, right? The sun is always giving us solar wind, but the quality, the intensity of it is really quite variable. So now let's think about Earth on the receiving side of that energy. All that energy is spewing at us, and we also have our own magnetosphere, which means that it provides protection at the equator to all of that energy, which is really great if you live at the equator. It's not so great if you want to see aurora at the equator, because that's where the energy is getting funneled towards our poles. But it's pulling that energy, and then how essentially the Earth that is, the magnet that is Earth, interacts with that energy, decides how and when we're going to see aurora. So let's kind of do this step by step. And there should be, there we go. They're kind of slow animations on their own, but they should kind of pulse through. Hopefully you guys can see them, but I'm going to walk through it verbally regardless. So stage one, we have our sun. It's emitting all of these particles. And when they come, they're going to hit Earth sort of right on this dense side here. And I want to use that wind analogy again. So think about, we're a magnet. The side facing the Earth has all of that solar wind and energy. Think about like walking in a rainstorm or in a snowstorm, and you kind of tilt your head into it so that it's actually denser, it's more compressed on the Earth facing side. And our magnetosphere is actually quite loose and relaxed on the leeward side because it doesn't have that energy pushed against it. It kind of relieve itself. So the energy comes, hits the sphere, and then our magnetosphere picks it up and sends it to our poles, just like iron filings if we were doing this experiment in class as kids. And when it gets there, this is the scenario where, depending on the range of energy, this is when you can see aurora in the daytime. Now, I'm going to make the caveat of that is that the only people who get to see aurora in the waking hours are if you're in the polar night. If you're above 66 degrees north, then you're at a high enough latitude that you can actually see aurora in the daytime. These are generally fainter. They can still be really nice showings, but they're not quite as bright as what would be our nighttime ones, because the nighttime ones we're going to see here in phase 2 or step 2. So now let's see that energy comes from the sun, but say it's got some more kick to it. It actually breaks those magnetic lines and causes them to backflip to the dark side of the Earth, just like Vader. No, I'm joking. I just wanted to throw in at least one Star Wars pun while we spent this much time talking about space. So they're going to go to the dark side of the Earth, and all of that energy is rebounding, and it's coming through. And so it breaks them, and it sends that energy, that plasma, those electrons, to the backside of the Earth. Very, very cool place to be. And think about it like beads on a string. They can't go anywhere. The energy is stuck on our magnetic lines, which brings us to phase 3, which is that eventually those magnetic lines are strong enough to reconnect, pull each other back in. And when it pulls it back in, it kind of slingshots that energy or that plasma back to Earth. It says, hey, you're still attracted to me. Come on back. And so that's the part where we're finally going to start seeing it here for you and I. Because when it brings that energy to Earth and it starts interacting with our atmosphere, then we start to see fun stuff. Right now, everything I've described to you is nothing you can see with the naked eye. We haven't gotten close enough yet. By the way, Earth's magnetic sphere goes out thousands of miles from Earth. All of this is happening thousands of miles to us, and it's looping that energy back into us. So it protects us from the most of it, right? If we got all of the energy from the sun that it sent at us, we would be a barren, desolate, sad little planet. But thankfully, our magnetic sphere deflects the vast majority of that, sends it off to somewhere else in space for someone else to deal with. And what we get back on the receiving side is just enough for us to have a beautiful functioning planet and beautiful aurora. So just as a recap, in case that wasn't quite moving through or the animation wasn't moving through the way I wanted it to. So we get solar wind coming in, and then if it doesn't have enough energy, if it doesn't break the lines, you can get daytime aurora. So again, they're happening in the daytime, just you won't see them unless it's polar night. Those are generally fainter. And then on the flip side, it has enough energy to break open that magnetic attraction and send it to the dark side of the Earth. So it's the leeward side. If we keep using that wind analogy, it's the leeward side of the solar wind. That comes around, they're going to loop back on themselves, rejoin, reconnect, because it's like a magnet, it's not letting go, pulls it back into Earth. And then when it pulls that plasma back in, that's when we start getting into the Earth's atmosphere. And again, chemistry was not my favorite. I made it through. Hopefully you can keep chemistry fun. And again, you can just enjoy the story of it. Don't get overwhelmed. These are our basic ones here. Some people like chemistry, some people don't. That's why I say that. Some people are like, this is great. Some people are like, this is the worst thing. This is like torture. Please don't show me this. So you can close your eyes if you don't want to look at the chemistry. But again, just really back to the basics. So this plasma, this solar wind, it's, just like when I'm breathing out, that's actual molecules are moving. Our wind is moving molecules around. The solar wind is moving around protons and electrons. But like I said before, they're not attached to each other anymore. There's so much energy that they're just ripped apart and they're just free floating. And so when they come to Earth, those electrons come and they start to interact with what's already there in the atmosphere. And that extra energy, that extra electrons jumps aboard who's ever there. Is like, woo, let's go for a ride. Let's have a good time. And so that's the difference between a grounded state and an excited state. And this happens on Earth. You don't need to be borrowing electrons from someone else. Just putting more energy into a system, it raises the valence level. And then when the energy leaves, it goes back down to a more stable level. Kind of the basis of it. So if there's anyone on here who's a morning person, you're someone who can wake up in the morning, you don't need any coffee, you just roll out of bed, go about your day, you feel great. People don't like morning people, or other people who need caffeine don't like morning people. They're just like, how dare you survive without caffeine? But this is kind of what stable oxygen is up in our atmosphere before any electrons come and hang out with it. It's stable, it wakes up in the morning, it goes to work, doesn't need any caffeine. I'm going to keep the caffeine analogy. So all those electrons are coming in, and we're going to talk about oxygen first in our atmosphere, but then we'll talk about a couple other molecules too. So oxygen's hanging out in the atmosphere, having a good time, and consensually or not, someone, aka those electrons, fill it full of a boatload of energy. It is like, oh my gosh, we are so excited, let's rock and roll. So we're going to say that oxygen can get receiving two kind of states of energy. It can get S state, which is like getting pre-workout mix, which is probably how much adrenaline I sound like I have right now. We're like, woo, woo, woo. Everything's going crazy and your whole body is wild, but it doesn't last very long, right? So pre-workout mix is we're going to call the equivalent of S state. You can go up, but it doesn't last long and you come back down. Whereas the D state is more like your coffee drinkers. They wake up, they have their morning coffee, they read the paper, and they're good for, they might not need their second cup of coffee till 2 in the afternoon, or maybe they don't even need a second cup of coffee, more of that slow burn energy. So these guys, if we think about S&D for a second, so pre-workout versus coffee, pre-workout are the ones that we see in green. So that's actually oxygen is what we're seeing. And essentially it only, it gets a bunch of energy, but it can only hold on to it for a second and then it lets it go. And that means that after it lets it go after a second, it lets off photons, which we see as green or green yellow, depending on the spectrum. And then the coffee drinkers, they need a little while. They're still waking up. They actually need about 150 seconds before they're going to let go of a photon. And they're the ones that we see as red. So they're more red. They're more rare. So you think that if we were to think about oxygen in our atmosphere and things like that, we've got a few coffee drinkers. We've got a lot of oxygen that just takes way too much pre-workout mix and gets real crazy and then calms down. So I'm going to add in one more. I've sort of imagined a game of this, of how oxygen is working. It's almost like I want to play a game of tag, and I'm going to call it Aurora tag. And the rules are that you have to stand still, and if someone else touches you, then you get their photon, and it calms them down. So you steal their photon before the light can go off. So anyone who has the pre-workout mix, who has the S level in their electrons, they only have to stand still for a second, so they can always give off their own photons. The red ones, they have to stand still for almost 3 minutes, which means that they almost always get caught, which means that you never get to see their own photon, which is very sad. And so if that was, we'll bring that into out of tag and into reality. So let's think about the order that we see things. The more people you play tag with, right, the more likely you're going to interact with someone else. So red is the rarest color that we see with oxygen, because in the lower atmosphere, which is sort of down here, anywhere under that 250 mark, let's say, in the lower atmosphere, in order to get that red, it has to be alone by itself for a long time, which doesn't happen very often. But if you go to the upper atmosphere, there's far fewer oxygen atoms, which means that it has way more time to hang on to its photon, drink its coffee, read its paper, do its things. 150 seconds later, it lets off a little red light. It's great because it's just thinner. There's just fewer. It's oxygen hanging up more on its own. The green is kind of below that 250 kilometers, getting close to that 100-kilometer range, or 60 miles or so. And so green, that's when it's the fastest players. They're able to keep going, firing off their photons, having a good time. Now, there's another one that I haven't talked about at all yet, and that's because I explained the more complicated ones first. Nitrogen. Nitrogen just fires immediately. Nitrogen is light, boop, gone, boop, light, boop, gone. Doesn't even need a second. It's almost instantaneous, which means that we get blue light from nitrogen. So on the lower end, if you're looking at Aurora and you see that pink, you're sort of seeing, the nitrogen firing off, and then it's mixing with actually some oxygen that had time to go. So that's why we need more energy to see more colors, because the density will last longer at a lower level. And then on the other end, we can see red rarely because it needs that high oxygen. So green is our most common, hanging out in the middle. It's also why nitrogen, when we see the pink on the bottom, sometimes people say it almost looks like the pink leads the green. And it does, because the pink is the nitrogen firing almost instantaneously, and then the other ones take a second behind it. And so you can actually watch a curtain shift, and you can see that those lighter colors, or the purple colors or pinks, leading the other colors. So if that was a lot, and you're like, oh my gosh, that was more about colors and lights I ever needed to know, here's the short version of that. Oxygen gives us reds and greens. Nitrogen gives us purples and blues. Then it just depends on how much they mix, is kind of the range that we see. Oxygen, high oxygen red, low oxygen green. And then purples we see above 60. Blues are rare too, also just because you're trying to see blue on black. So it's harder to see with your eyes. And so you can see some absolutely phenomenal different colors. You can sometimes even get spectrals of yellow if you're getting a more pure oxygen sometimes too. Just depends on that sort of mid-latitude one. There's lots of beautiful different colors. And having worked different seasons going up to Churchill, people will get there and they're like, this doesn't look like what it sees on the camera. And you're right, folks. It will never look the same as what it does on your camera. I can also say that for myself, I have stood there and seen the colors you see on a photo in real life, right? but those are rarer because you need those larger storms and things like that. And so it is definitely an expectation management one. And there's the second part of this. There's both the camera will never, you will never see what the camera sees, because the way that we take in light and the way that it takes in light are vastly different. They function different things. And the other thing is that between me or myself and whoever is out watching us here, none of us will see them the same. Now, obviously, we kind of have the notion that everyone sees color a little bit differently. My version of green is not your version of green, but it actually goes even one step further than that. So I want to talk about our eyes for a minute. We are a super visual species. We do most of our communication visually. There's all these things, right? So there's layers to understanding how our vision works, which is going to understand how you as an individual person are going to be able to engage with the aurora. So first of all, we've evolved to be able to see in relatively varying degrees of light, so dimness and darkness, better way to say that, but you know what I mean. And then we also have the ability to see color, right? Not our dogs and all see color, which we're very, very lucky, very grateful for. And if we go into the structure of the eye, that again, it's probably getting to familiar territory, but we're talking about rods and cones. So in a human eye, there's around 90 million rods. These are the ones that are able to see in low light. Actually, they function best in low light. And they are way more sensitive to light than the cones are. They also have another fun quirk, which is that rods don't react to red light. So anyone who is coming to see aurora, if you're watching this and prep and getting excited, if you don't already own one, and actually this is just a general thing for anyone listening, but buy yourself a red headlamp or red white light switching headlamp. There's a zero white light tolerance once we're up viewing aurora, and it has to do with how long your eyes take to adjust. So your rods need actually about 40 minutes to fully adjust to night vision, which is a long time. So every time you reintroduce white light, you're having to reset and slow down your capacity to have night vision. So everyone, just buy yourself a red light lamp. Be great for your night vision. It'll do good things. Okay, your cones, on the other hand, this is your color, right? We're talking about your primaries. They're going to be able to see green, red, blue. There is about 1/15, so there's only about 6 or 7 million, excuse me, cone cells as there are to rod receptors. And so there's fewer of them, and also they need brightness. So in order to see color, we actually need light. If it's not, then they don't turn on. Now, the plus side of cones or different skills, so different contrasts, is that they don't need 40 minutes to set up. They need a second or two. They react much, much, much more quickly. So not only do you and I see different greens just because of who we are, but there's also something really important that happens in everybody's body, is that we actually decrease the number of rods and cones with age. And so, and not only that, but the cells that you have can become less sensitive to light, which means that they reduce their function. So what does this matter for you and I when we're looking for northern lights? It's that and this has happened to me, I've had 10 people standing in a group. We've all been looking up in the northern lights. And if you ask the group, 4 of them will say they're white and 6 of them will say they're green, because the ratio of functioning rods to cones in their eyes are such that they can't actually see the color. And that's a really hard one, right? Because everyone is there sharing the same experience, but their bodies aren't able to see it, which is of no fault of anyone. It's just where we're at in life. And also, there can be younger people that also, but just as you get older, it gets harder to see the colors, and you need more brightness in order to activate your cones, right? So we talk about pros and cons. Everyone's like, oh, well, you want that perfectly dark sky in order to see aurora. And on one hand, yes, that, if you have a really amazing storm, which is kicking off lots of energy, then you're going to have bright aurora and you can see them. It's great. Sometimes you can actually see more color if the moon is out, because the moon is giving enough light for your cones to see the green, right? So it's not this pun intended black and white of what are the best conditions to see them. It really does depend on the person, on the scenario, and what is the best night for the person to my left might not be the best night for the person to my right, even if it's the same aurora, right? So something to think about going forward here. And also, again, sort of the colorblind thing, but if you can't see a number in this circle of dots, it means if you haven't already, you should get your eyes checked, because this is a little colorblind test that I left in there as a fun little aside. Okay, it's a good thing I didn't add on the other topics. We're doing, or how are we doing on time? Oh yeah, we're good. Okay, so far I've kind of talked about why the aurora happen, and talking about the eyes is kind of like who, hopefully that's you, will be seeing them. And I'm going to try and cover in the remaining time a little bit of the what and the where and the when of the aurora. So, I mean, really, what are you going to see when you see the aurora? You're going to see one of the most beautiful things on this whole planet Earth, in my opinion. I guess it's not on Earth, but you know, it works. We're on Earth. The view is up. But we do, it's the same as any form of art. You know, if you study, or is that a right way to comparison that? I'm not sure, but I'll stick with it. If you study art long enough, you have terms for it, right? Well, this is a Renaissance painting and they use this brushstroke, and you know, anytime we work on something long enough, we give it terms. You can also just say that it's beautiful and you don't have to learn any of the terms. But if you are curious, or you want to be able to describe something with a common language, which is ultimately why we give something a term, so we can share an experience and understand one another. So we tend to group aurora into 5 different general shapes. And even as you can see from this picture here, is that it blurs one into the other, right? You know, how much of a difference is it really? But if you study these long enough, then you get more nuanced with it. So arcs is simply a simple curving structure, and that usually has a smooth lower border. We call something a band if it's continuous, but it's irregular. So the bottom border, which is often the brightest of the light formation, and it can have kinks and folds. We say patches, which is often usually when the auroras start waking up or kicking off, as we just start to see patches here or there. And those are just small isolated regions. These are the ones that we most mistake for clouds, because you'll look and you're like, is that a cloud? Is the aurora? If you're ever asking yourself that and your eyes aren't able to pick it up just yet, that's when you use your camera. You take a picture of it and you're like, oh yeah, that's green, right? And then you know to start mobilizer, you know to stay up later because the show might start off. We also have veils, which are sort of like the veil between this life and another. I don't know. It's the least distinct. It's just kind of a general haze. Again, kind of an easy one to mistake for a cloud, but this uniform, and it takes over a large portion of the sky. So that's how you would distinguish between a veil and a patch. And then rays are what we use to describe vertical shape. So that's they're following the magnetic field of the Earth. So those are the 5 basic shapes. And then when those shapes start to intermix between each other, then we get other things, right? So a curtain is a rayed band. It's an irregular shape that has light flowing upwards. Corona are when I think it's rays converge, and then you get these really crazy looking storms. So it's just like weather, right? We have cirrus clouds and cumulus clouds, but again, clouds can mix and have different shapes. So it's a good parallel of that, and it can get really blurry. But those are kind of how we'll talk about it in the field. We can also talk about their behavior and how bright they are. So if we think about behavior, we often say they're quiet, so it's very subtle. We can say pulsing, so it comes and goes. Flickering will last. You get 5 or 10 minutes of a great show and then it disappears. And the thing that we're hoping for often when we're traveling to see the aurora is flaming. When it's just bursts of luminosity and it's moving so quickly that you can't, like, it looks like real fire, right? You can't really believe that it's moving so quickly. And then we can also talk about the brightness of it. So there is actually an international brightness scale that we can use to compare it back to. So 0 means that it's only detectable with instruments. So no one's yet, bothering to go stand and freeze in the cold. 1 is that it's comparable to the Milky Way. So it's kind of whitish, but it's not enough light to see color yet. So again, go back to thinking about your rods and cones. Even if you have the best, even if you still have the healthiest eyes or the best ratio and they haven't degraded, even you would still see them as white. And then 2 is when we start counting them as visible. So that would be the same as starting to see them as yellow-green. And then 3 is when it would be like a bright lit, it's the equivalent of moonlight kind of thing. And then 4 is when it's almost like casting a shadow. Like the aurora can be bright enough to cast a shadow behind you, which I hope is something that everyone gets to experience someday, because it just kind of feels like a childish sort of joy or experience there. And something I want to remind everyone as we've been going through this, because at least I'm in the Northern Hemisphere and I'm about to leave for Churchill in a few days here. So this has all been Northern Hemisphere centric, but everything you see in the North has an instantaneous twin in the South. We just talk about it less because when you look at the land mass between North America and South America, there are far fewer people around. There's some folks on ships and there's a few research bases in Antarctica. But besides that, it's just far less likely to see them. They're not happening less often. They're happening with the same degree in magnitude, because remember that energy gets sent polewards and then loops back and flips on itself. So there's always a twin. Just, send a hopeful thought that when you've got a great show, hopefully someone else on the other end of the earth is seeing it same place, same time as you. And if you're curious, what will the aurora look like tonight? I don't know. Fine, you could be able to tell you that. I would have a different job and potentially make much more money. We never know, right? It's how those current solar winds are interacting with our magnetic field. It changes from moment to moment. This is why it's been one of the most elusive things to study. You can't capture it. You can't put it in a bottle. You can't really predict it super well. You can predict magnitudes and, to a certain extent, but it's just like real weather. At the end, you just have to be there to experience it. You'll never know otherwise. I can, with considerably more better than this, I don't know, talk about when we will see them. I can do a little bit better to help us out on that one. So first, just on a really big temporal level, is that we're going to go back to one of the other mysteries of the sun. The sun flips its poles every 11 years. North becomes south, south becomes north. And when that happens, when that flip happens, we get crazy solar storms coming off of that. We get more solar flares. We're located next to sunspots. We just get more solar activity, and so we get bigger. It's like hurricane season for the sun, if you want to make that comparison, or monsoon season, whichever one you want to use, right? So we get all this crazy energy, and then there's a quiet season, and then we get the crazy energy when it flips again. So we're coming off of one of these solar maximums that would have kind of been hanging out at like 2024, 2025. We've done the flip. We're on the way down from the maximum. Good thing for us is that, or at least in these next couple of years, is that the solar maximum ends, but then the aurora activity lingers for another year or two afterwards before it starts going down. So we're at a good spot for that. I will say, even if you're in a solar minimum, it doesn't mean that you won't see them. There's still, remember, it's just like weather. There's always wind, right? It's never not there. There's always solar wind coming at us. We just have less of these really large magnitude storms. So it's just a different kind of solar activity that leads to it. So we can look at this, and we have been tracking this on really long time scale. So this is kind of cool. This is showing the number of sunspots. That's one of the ways that we know where we're at in our solar cycle. We get lots of sunspots. So again, lots of that tangled magnetic energy where if it's too tangled, snaps, breaks, sends us a max ejection, which is great, gives us something lovely to look at. And we can track that, and we can sort of compare that. This one is showing us from 1965, and it's doing some projections into 2030 here. So we're just hanging out post 2025. And that's kind of the number of sunspots you could expect in a year, right? So we actually weren't, compared to the 90s and 80s, pre my time, or at least the 80s would have been, was some really good time to see it. And then we're higher than we were on the last cycle. Excuse me. We are higher than what we were on the last solar cycle, that 2010 kind of 2015 peak. But we're doing pretty good here. So we're in a nice window. And even if, let's say, you hadn't planned to go until 2030 to any of these places or any of that, it's okay. There will still be aurora. It will just have, every night will be different. That's really it, right? You just have less magnitude, and then it's also sort of less odds. But you can still be, the further north you are, you don't need these crazy storms. You're already there, right? Even good weather is great aurora if you're far enough north. Maybe that's the right way to say it. So that's on this big yearly cycle. Now let's talk about actually just seasons within Earth. It actually matters what time of year to be able to see aurora. You can see them any time of year. I've seen some freaking cool ones in August and July. But in general, we see them best spring and fall. It has to do with something which I think is called the McPherson effect. Give me 1 second. Russell McPherson. There we go. And so essentially they figured out that the tilt of the Earth and relative to the sun, there's an ideal angle when it gets to our poles, and we want it to have the most, we want it to be in opposition. So if Earth's magnetic field is lined up with the solar wind, we get weaker storms. If the angle of the Earth is tilted against it and they're opposite, then that, we'll just say that disagreement creates more of electrical charge or an exchange, and we get more excitement and better showings. So we tend to get around the two equinoxes. Spring and fall are great times to be able to see aurora. Okay, let's keep narrowing it in here. Keep track of the time. It'll go a little bit longer here. Why Churchill, right? Why are we doing so much effort to get ourselves up there? Well, it has to do with us, where we're located sort of on the Earth. And this will again fit into a bit of that what and that where, or that where and that when, I should say. So if anyone has gone or looking for the aurora or has been trying to predict the aurora, one of the things we often talk about is KP index. This is derived from German, which I am going to butcher. Planetarisch, I can't even say the last part. Planetarisch, Kennziffer. Anyways, it means planetary index is what we've translated into English. My brother speaks German. He would be very upset with how badly I just did on that one. Anyways, the idea being that what degree of a storm do you need for it to be able to see it at lower latitudes? So it's ranked on a scale from 0 to 9. And this is kind of a cool map if you're able to see it, because these are really extreme storms that have happened, or aurora viewings that have happened through history. Like you can see one here in Spain in like 2003. We can see one down here in Greece, right? Like we've got some that are happening, again, some historical ones I've kind of walked through before. There's one in Africa. So they do go lower than that, but you just need a really big storm for that to happen. So 0 doesn't mean that it never happens. 0 means that it always happens there. So it means that if there is a regular solar wind, which there always is, you can see it here. You don't need any more to see it at a lower latitude. So the KP index is useful for thinking about a degree of solar storm, but the further north you go, it's arguably less useful, because it just means, yes, we will see it tonight if the weather is clear. So that brings us to Churchill. So this is another way of looking at the same thing. That was kind of from a European perspective. And so this is your percentage chance of seeing it. So I don't know if you guys realize this, but if you go straight to the North Pole or to the geomagnetic North Pole, it gets weaker, right? There's actually the 100% chance of, if there's aurora, we will see it, is hanging out around this latitude, which I forgot to put a little pin on it, but right here, oops, hopefully you can see my arrow. That's Churchill. We're right in that 100% range. There's a few other places that are. There's some places in Norway, places in Alaska. This is why these locations are so prime for seeing aurora, because they are in that belt. And if there's aurora to see, they're going to have a chance to see it. So we're getting closer. We're narrowing. So we've narrowed in on where in the Earth you want to be for having the best odds. We talked about yearly time, seasonal time. Now let's talk about daily time. I got done saying before that you can see aurora in the daytime, right? You need to be it needs to be polar night, and so you need to have no sunlight in order to see it on the sun-facing side. But that magnetism, and again, go back to thinking about leaning headward into that really hard wind. In this case, it's solar wind, and our Earth's magnetism is pushing against it. So that's getting sent around to the backside. So the strongest part is always the midnight side. It's always the furthest away from the sun, has the strongest aurora showing, and then we're just turning through that, right? So early evening is generally quiet, and then it really does get more intense later at night, and then it chills out again later or as we start to get to the next morning, right? So we're always going through that cycle. And again, I'm saying this is a general rule of thumb. You can have crazy aurora at 6 p.m. You can have crazy aurora at 6 a.m. It just kind of depends on light and availability and all that jazz. So, and I'm almost done, I promise, Rob. I got a few more slides. So when we think about aurora, and we think about trying to see this in where we're going, into Churchill, this is the overall sort of aurora best viewing for Manitoba here. And the reason why, I just got done saying that you can see it really great in the spring, and you can see it really great in the fall. But if you look at what Manitoba, that's the province that Churchill is in, has as a predicting for seeing aurora, we tend to veer just towards the spring side. And that has to do now with more local weather. It's not that there's not great aurora possible the rest of the year. It's not that it's definitely not possible in this fall window. The kicker is now you have to think about local weather, right? So we have when freeze up is happening in the fall, there's still crazy amounts of clouds. Our weather is more unpredictable. Whereas for better or worse, once you get through the heart of winter and start coming out the other side, it's clear, crisp, bright, and that is exactly what you want. You get these, very cold days, but that coolness also means there's no moisture in the air, which means you have the best chance of seeing it. So that's kind of why this sort of, and we're gearing up for it right now. We're right on cue. The first trip has just kicked off. The first Churchill trip started on the 15th or the 16th. I will be going up there for the 23rd, right? And then it kind of tails out in March. So we sort of built it around that prime time to be up there. Obviously, there's always a little bit of wiggle depending on weather that year. Okay. There was one other thing I want to get to, but I will close it up here just to respect everyone's time. So I hope that what you've gotten out of this is that, space weather, very cool, but just that Aurora is going to be different every single night, every single time. And that's what makes it fun. You think about going to see wildlife and it's sort of that chase, but the Aurora, you are kind of chasing it. And they do call them Aurora chasers sometimes, but it's never the same twice. They're just like snowflakes. They're always amazing. And the nerdy thing I wanted to say is a quote from the Thor movie from the Avengers of the Wild Goats. Like, your ancestors called it magic, but you call it science. I come from a land where they're one and the same. And I kind of think that's what the Aurora are, right? It's kind of where even the science is so cool, or the science is so unbelievable, that it starts to feel like it's actually magic. So with that, maybe I will end it there and pass it back to Rob.
All right, Kristina, thank you so much. All right, so if you do have questions, I'm going to remind you, you can submit them via the question field in your control panel. So let's dive into some of these questions because we do have a couple. Let's talk about radiation particles. How much radiation is contained in solar winds? How does the Van Allen belt interface with these particles flowing from the sun, and what happens to the particles contained in the belt during a magnetic reversal?
Oh man, is there a physicist on the other side? You got some heavy hitting ones.
I
No,
know,
that's
huh?
great. I don't know all the answers to this, so I'm going to answer ones that I can. I don't know the ratio of radiation coming in at us. And again, so there's like the tricky difference between solar energy and solar flares, but so if we just look at this last picture I've got on the side, so these blue lines are what our friend here is talking about, the Van Allen belts. I didn't give them their name this whole time, but those are those magnetic lines that interface with the energy coming in from the sun, and then pick it up and either redirect it to our poles on the day side or redirect it eventually to the night side. And those are the things that are diverting some of that radiation and some of those particles and some of those energy. I don't know the proportion, sorry, offhand, of how much radiation is deflected versus how much actually comes to Earth. To my understanding, it's like very little. It's still a crazy amount of energy to us, but retrospectively, it's a lower portion. I'm sorry, I don't have the exact number on it. And there was a third part to that, Rob. Sorry, there was the
What
radiation, the Van Allen belts, and was one more.
and just what happens to the particles contained in the belt during magnetic reversal?
Okay, I'm gonna assume when you say magnetic reversal, we're talking about the Earth's magnetic reversal. Because the sun does one and the Earth does one. And I'm not sure if we're thinking about for ours during that time, whether or not the bands would be less structured. So I didn't bring this up in our talk, folks, but our very well-informed friend on the other side, if they're talking about the sun, that's what I was saying, where we have the 11-year cycle. We do a pole reversal as well, but I think ours is on the scale of like tens of thousands of years. And so when we flip, it does a bunch of crazy stuff to our Earth too. So we have like there's different events that are tied to that sort of, and so it can. I don't know radiation wise. Oh, actually, sorry. Some of this I do know. Hang on, dots are connecting. So when they were trying to track down the earliest studies of Aurora, earliest stories, there's a theory. This is just a theory. This is not a confirmed one, but it's kind of a fun one where like anthropology and astrophysics overlap. They have a theory that a lot of these cave drawings are actually of aurora that would have been seen tens of thousands of years ago when Earth was going through a radiation flip. So the theory is that when Earth is doing a magnetic reversal, you would get aurora like at the equator. Like we would have I don't know if it would last 1,000 years or what it would take. You're kind of getting outside of my knowledge about. But the theory was that when this reversal was happening, a lot of like early humans would have seen wild shows of the aurora all around the Earth. And so that's kind of one thing. None of us will be alive to see it, but hypothetically, the next flip could have a really intense show. So there's one thing. I don't know other radiation-wise, but that is one cool crossover.
Perfect. Thank you for tackling that very difficult question. He was talking about the Earth reversal, so that was great. Thank you. So now, can you explain again how a red light on a headlamp will help us adjust to the darkness?
Yeah. So when our rods and cones, when you think about them being able to turn on, so rods work best in low light, whereas our cones work best in bright light. And so if we want to be able to pick up the small signatures of light, which is what nighttime is, right? Yeah. We don't want to be constantly turning our rods on and off because our rods will actually disengage. If you turn a bright light on, the rods will say go to sleep, which is not helpful for being able to see in low light. So the difference is that red light versus white light, that red light doesn't shut the rod off. It doesn't close it down. And so it keeps running and it keeps seeing everything. So that's the benefit of that. If you want to have good night vision, you don't want your cones necessarily to be operating crazily. And I know this is there's a bit of a push and pull here because you do need enough of your cones turned on to see color, right? And then it kind of depends on the individual person of what that proportion is. So it's a bit of a dance, but in general, you want good night vision, which means you don't want any white light kicking in, and especially not really intense white light. Yeah, that's the balance there.
All right, so we've had a couple of people ask if older people can't really see the aurora as fully as younger people, is it worth going up there to see it? Should we just take more pictures? Would it be easier to see on a computer?
Here's the thing. I don't know what your eyes are going to be. I'm like, for me, so for each individual person, it's the same thing. I don't know if I'm at 0 or 100. I know that myself younger had a better chance than seeing older. It's not saying that you're not going to see them or that you're not going to see color. It just means that you might need to see a brighter show to see them at an older age. And I will say this, the amazing thing about the aurora is never captured in a photo. I love taking pictures of them. It's stunning. It's not in the photo. It's in the movement and it's in the mass. It's the same reason why I like to go to the theater rather than watching a TV. When you watch a TV, all that you can see is what you're told to see, right? You're told within this fine line, you're focusing on the characters. When you watch theater, you can see like other characters are doing things in the background, and there's this whole other world happening, right? Same thing as with aurora. It's your whole peripheral vision taking everything in. And I mean, it's the stimulus, it's the smell of the trees and the snow. I mean, all of that is part of being human and being there. But the cool thing about the aurora is that it's this full takeover. So I would never say don't go. If it's on a dream, it's on your plan to go, it might mean that you have to go twice. It might mean you have low odds of having that really great showing. I will say this, based on that brightness scale I was talking about, once it's a good geomagnetic storm, everyone sees them. I shouldn't say everyone, but like I might see a little bit more pink than you might see the green in that way. But once we get above that 2 in that international brightness scale, if we get to a 3, you're all going to see green and it's going to be really cool. It's just in that lower range that color of eyes matters. So like, for example, polar bear season, we do get lights, but we don't get them nearly as bright as we do coming into aurora season. So it's more of a discrepancy there. If you have a great show, everyone will have a good chance of seeing it. So that's, yeah, I hope at no point did I dissuade you from trying to see the Northern Lights.
No, you've explained it perfectly this time. Or I get it even now too, so we're good. I may experience them differently from somebody else, but I will experience them in some way. So that was well explained. So thank you. Well, Kristina, that's going to be the last question that we do have time for today. So thank you for this. I'm going to throw it back to you for some closing comments.
Thank you, everyone. Thank you, everyone who tuned in for all of the different parts of this. It's been a pleasure to get real nerdy and deep dive, and hopefully done my best. It's always, if you learn it to teach it, you learn it for yourself. So it's the gift that keeps giving. And if anyone does remember from the very first one, this was a quote I had in the first presentation. It's that the universe is not made of story, or is made of stories, not atoms. And I kind of nerded out and sort of alluded to it before, but it's both, right? I think we try and take the science out of the story or the story out of the science, but what's really cool is that the aurora are this amazing example of all of it coming in together. And that sometimes the science in the story can be as beautiful as the mythologies and all of that. So thanks everyone for coming on the ride with me.
Kristina, thank you so much for taking the time to present for us today and for the entire series on auroras, which you can catch up on our website at nathab.com/webinars. See all 3 parts there. So I'd also like to thank everyone who joined us today. If you are interested in information on how you can travel to see the Northern Lights with NatHab, please give us a call at 800-543-8917 or send us an email at info@nathab.com. Our adventure specialists are happy to help you out. Join us tomorrow for our next Daily Dose of Nature. You can check out this week's lineup, including registration links on our website at nathab.com/webinars. We did record today's presentation, and the replay will be available on the website soon. With that, I will conclude today's webinar. So long, everybody. We'll see you next time.